everyone. Yeah, thanks for coming. So this is the workshop for machine learning for algorithms. It's covering basically how we can use machine learning in design of algorithms and data-driven algorithms, learning augmented algorithms. And it's organized by Avrim, Nina, and Piotr and me. So yeah, and just one important thing is that tomorrow we have a poster session. So we have 2 talks and then a poster session, and the poster session will be here. So for those who are also presenting, please come early tomorrow in the morning. We can set up the posters. So without further ado, I mean, the first talk is by Nina Balcan, and she will talk about machine learning for algorithms. Thank you.
Okay, thank you. Okay, cool. So thanks everyone for coming early in the morning. So we'll be talking about, I'll be talking about machine learning for algorithm design. And really, this will just be an overview of how you might provide provable guarantees for these machine learned algorithms via dual function classes. Okay, and since I'm the first talk, I will also start by giving a little bit of a high-level overview of what this field is about. So obviously, everybody in this room knows what an algorithm is. It's a finite sequence of precise step-by-step instructions to solve a well-specified class of problems. Concrete problems to keep in mind could be like algorithms for solving combinatorial problems, like clustering problems or partitioning problems, maybe pricing, auction design problems, logistics, scheduling, and so on. Any type of algorithmic problem you might think you might really want to solve. And the key point, and of course, these problems have been studied for many years in many different fields, like theory of computing, operations research, economics, and so on. I guess the problem is that many of these problems still remain hard in classic frameworks. Okay, and what do I mean by classic frameworks? So here is one way you can think about it. So especially in theory of computing, the classic way to design and analyze algorithms is, is to consider hand-designed algorithms. So if we have a problem that we want to solve, the traditional way to think about it is that we fix our problem, and then we have a genius scientist, any of you in this room, maybe Yuri, Piotr, Avrim, any of you in the room, the traditional way of thinking is, well, this genius scientist sits down, has a stroke of genius, and hand designs an algorithm for the given algorithmic problem. And then, from an analysis point of view, what historically in theory of computing we have been thinking about is worst-case analysis. So in particular, the type of guarantees we are thinking about is how well does the algorithm do on a one-time, one-shot, worst-case instance of the problem. Okay, now when it's possible to have hand-designed algorithms that have great worst-case guarantees, that's fantastic, it's amazing. But unfortunately, many of the problems that I mentioned earlier are actually, the guarantees that we can get in these classic frameworks are kind of weak. And they're weak either for solution quality or for runtime or for your favorite performance measure. Okay, and as a consequence, what people do in practice, rather than using hand-designed algorithms with poor worst-case guarantees, what people in practice do, and what they've been doing for many years, they have been trying to incorporate somehow machine learning into algorithm design. Okay, this is the term a couple of years ago, or maybe 5 years ago. Now, of course, people talk about LLM for algorithm design, or even agents for algorithm design. No? So as AI is evolving, the terminology evolves as well. And this kind of makes sense, but of course the key question, especially for the STOC audience, is whether we can provide any provable guarantees for these machine learning based algorithms or AI-based algorithms. And I guess I want to, again, point out that using machine learning or AI for algorithm design makes a lot of sense. Why? Because in practice, we often need to solve not only one instance of the underlying algorithmic problem, but we need to repeatedly solve instances of the underlying algorithmic problem coming from a certain domain. And also, in practice, sometimes different algorithms work better in different settings, so it really makes a lot of sense to use learning and instances of the problem coming from your domain to learn an algorithm that does well on your type of instances, in particular in your domain, rather than worrying about worst-case instances. So, I mean, the idea is very, very natural and has actually been studied empirically for a long time across different fields, like in AI. So, for example, work going back to 2000s by various people, including Kevin Layton Brown, who will be one of our speakers later in the week. So people have considered this in AI, also in algorithmic game theory, computational biology, and so on. So there has been a lot of empirical work and increasing in popularity empirical work on the topic, but very little theory. There has been some theory, so even 20 years ago, for example, if we go back, there are some works, kind of scattered works here and there, like, for example, with Avrim and Isha Mansour and Jason Harline, we had a paper called Mechanism Design via Machine Learning in Fox 2005, but it was a very specific setting for auction design. So basically, while there has been a large body of empirical work, there has been very little theory work, because theory of computing has still been thinking about worst case and designed algorithms. But luckily, in the past few years, there has been a lot of exciting theoretical work on the topic by the organizers of this workshop and many other people in the room. And so now we have much more principles and more general tools for thinking about these data-driven algorithms, or algorithms for which we use machine learning components. Okay, and I just want to point out that there are two kind of major paradigms that have been developed. One of them is what has been called in the literature data-driven algorithm design. So here the paradigm is as follows. So we fix the problem that we want to solve, and then we also fix a large parametric infinite family of algorithms for our problems. And this parametric infinite family of algorithms might have various components, like every components, like dynamic programming, greedy components, and so on. And then what we do, we take instances coming from our domain for the given algorithmic problem, and we directly learn an algorithm from this large parametric infinite family of algorithms. And of course, the hope, and this is what we end up proving theoretically, is that if we learn an algorithm that does all over the past instances, that algorithm will also generalize on future instances. And so there are very interesting sample complexity questions that arise here. And by the way, this is an overview at this point in time, so we're going to see details later. But intuitively speaking, this type of sample complexity guarantees asks the question of how large should our sample of typical instances be in order to guarantee that good performance on past instances translates on good performance on future instances. So if we learn an algorithm that does well over past instances, does it generalize? Does it do well on future instances? And here many interesting sample complexity guarantees have been developed. And this is what a lot of my technical part of the talk will be about. Now, I want to point out that the underlying algorithmic goals now suddenly become a little bit different from the classic algorithmic goals. So, like, we want to learn an algorithm that does well over past instances, and we want to prove it does well, will do well on future instances. But kind of the underlying algorithmic problem, in a way, becomes even harder than the classic one, because we want to find an algorithm that does well on average over a training set of typical instances, rather than finding an algorithm that does well on just one instance, as in the classic framework. But of course, the catch is you have to solve this problem only once. So at the training time, at the test time, you don't have to resolve it. But the underlying algorithmic problem becomes potentially slightly harder, and Avrim's talk will be above it. So he's coming right after me, and he will talk about it. So you'll see in Avrim's talk more about the underlying algorithmic question in data-driven algorithm design, and I'll present very general tools for sample complexity analysis. Okay? And I think the third talk of the morning is by Ali, and he will talk about another paradigm that also falls under the umbrella of machine learning for algorithm design, and this is algorithms predictions, or learning augmented algorithms. And so what are these algorithms predictions? Here we want to design algorithms that take advantage of possibly imperfect predictions of some aspect of the problem. And sometimes these predictions, people motivate them as being machine learned predictions. And so the typical analysis that Ali will talk about a lot is like some trade-off between consistency and robustness. So consistency meaning, you do better than the worst case analysis when the predictions are really good. And robustness means you never do much worse than the optimal worst case cost. And so there's been a large amount of work in this direction for many different algorithmic problems. I do want to point out that from my point of view, it's also very important to also consider, if the motivation is that these predictions come from machine learning modules, it's important to also consider learning predictions, as well as the interplay between learning predictions and the design of algorithmic predictions themselves. And so in a way, I think it's very desirable here to have end-to-end guarantees. So a lot of the work has been focusing, if I have predictions, how do I use them? But these end-to-end guarantees are still very important, and there is a lot of work to be done there. And we have some work in this direction. For example, we had a New Lips 2022 paper in this direction, but it's still for more specific cases, not very general theory. Okay, cool. And so you might be wondering by now, so yeah, we can use machine learning for algorithm design, and this has been empirically successful, and now there is some very cool theory. But you might wonder, well, but machine learning and they are these very powerful tools, so why is it hard at all to even provide guarantees for these machine learned algorithms? Why isn't this just a classic machine learning problem, and there is a whole large field called learning theory, but maybe we just, guarantee just apply to this case as well? And the answer, well, is we are learning much more complex objects than we typically do in learning theory. And in particular, the corresponding loss functions when we learn algorithms are volatile. So, because these algorithms have modules that are interconnected, maybe they have combinatorial inputs, combinatorial outputs, a slight change in the hyperparameter of the algorithm can lead to a very different outcome. So in the end, the corresponding loss functions can have many, many sharp transition boundaries on many, many instances. And so they're much more volatile than the type of loss functions we typically consider in machine learning theory. So in other words, working on machine learning for algorithm design and providing provable guarantees from a learning theory point of view has led to very cool results from a learning theory as well, and has helped build and expand significantly theoretical foundations of machine learning as well. Okay, cool. So this is kind of a brief overview of this area. Now I'm going to go ahead and try to give you a few more technical details. And I'll really focus on more on data-driven algorithm design and tell you some sample complexity guarantees. I'll focus on the general sample complexity guarantees via dual function classes. And while these techniques have originally been designed more for the data-driven algorithm design, where I'm directly learning an algorithm coming from an infinite parametric family of algorithms, I think they also have implications for the area of algorithm predictions, and hopefully those can be further considered. Okay? So now I'm going to go a little bit more technically. And so again, we are thinking now about, so the paradigm to have in mind is the following. So we're thinking about, say, data-driven algorithm design. Now we fix an algorithm problem that we want to solve, and then we fix a large infinite parametric family of algorithms. Again, these algorithms could have modules, like your favorite kind of algorithmic modules, like dynamic programming, maybe greedy. And some of these modules might have hyperparameters that you can hope to tune based on past instances of the problem. And then we assume that the algorithm, that we also, at the training phase, we assume that we have access to some set of typical instances of the underlying algorithm problem. So for example, if we are doing clustering, we might have access to a number of past instances of the clustering problem. This could be instance 1, instance 2, and so on, and I have access to several of them. Or if I'm doing pricing, again, I have access to past instances of the pricing problem, or maybe, for each of the bidders, for each of the M items, I know how much the bidders value each subset of the items. And similarly, if I'm doing some sort of a knapsack problem, again, I have access to past instances of the knapsack problem. And now based on, so I fix the large infinite parametric family of algorithms. I have access to past instances of the problem. And then what I do, I want to do based on these instances, I want to output an algorithm from my family that generalizes, does well on future instances. And so this is when this sample complexity question immediately arises. How large should the training set of typical instances be in order to guarantee that algorithms that do well over the training set of typical instances will do well on new instances? Because the training set is very, very small, maybe there is no generalization at all, but as the training set becomes bigger and bigger, we can hope to generalize. And the question is, how large of a training set is enough to generalize? And now, at a very, very high level, yes, we can use tools from statistical learning theory and empirical processes to think about this question. And in fact, we know at a high level from statistical learning theory that the number of samples we need to generalize depends on how intrinsically complex the relevant class of functions is. And what is a relevant class of functions here is a class of functions induced both by the algorithms in our family and by the performance measure that we consider for the given problem, like runtime or solution quality and so on. And so we know from learning theory that, if the number of samples we see in the training set is of this order, the intrinsic notion of complexity of the relevant family of functions over epsilon squared, then that's sufficient to get kind of epsilon uniform convergence, which roughly speaking means if I find an algorithm that does well over the training set of typical instances, I compete with the best algorithms in the family. I do within a factor of epsilon, the best algorithms in the family. And in very intuitively speaking, if you've never seen learning theory before, this notion of complexity just captures the ability of the function in the relevant function class to fit complex patterns, because the more complex patterns you can fit, the more complex instances you can fit, the more samples you need to generalize, the more instances you need to generalize. Okay, this is very intuitively speaking. Okay, and for the rest of the talk, I'm going to show you like how, because the key, so we're going to build on such results from statistical learning theory, but the key point is now to analyze this interesting notion of complexity for functions, classes coming from data-driven algorithm design. And I already told you that function classes are very wild. They have many sharp transition boundaries on many instances. Okay, so for the rest of the talk, I'm going to tell you how to analyze this notion of dimension for data-driven algorithm design. Okay, and at this point, I'm becoming a little bit more technical because you probably want to see, so I'm going to tell you more technical details. So I'm going to now become a little bit more formal because now I'm going to present to you a general theorem that is applicable very broadly. Okay, and here is the kind of the abstraction. You know, it's kind of like first what I'm going to do, I'm going to put down kind of a statistical learning theory style framework for data-driven algorithm design. And along the way, I'm going to introduce dual and primal function classes that are important for my theorems. Okay, so what we're going to do, we're going to fix an algorithm problem that we want to solve, maybe subset selection or clustering or pricing or your favorite algorithm problem. So you fix the problem first. And then I'm going to denote by pi the set of problem instances for this problem. And then I'm going to denote by alg a family of algorithms for solving my problem that is parameterized by some set P, which is a subset of R to the D. So each algorithm is parameterized by D real valued numbers. And I'm going to know by A alpha, subscript alpha, the algorithm in the family of algorithms parameterized by the parameter alpha. And now, to make things formal, because so far I've been informal, I need to also fix a utility function. So the utility function goes from the set of problem instances times the set of parameters and goes to the boundary interval 0h. And so here, U of I and alpha measures the performance of the algorithm A alpha on the instance I. So there is this utility function that takes as input an instance of the problem and an algorithm parameterized by alpha and tells me how well the algorithm A alpha does on the instance I. And then I can also, when utility function then immediately induces the function U of alpha that goes from the set of problem instances to the boundary interval 0h. And this is just the utility function of the algorithm A alpha, right? So U alpha applied to instance I is how well the algorithm A alpha does on problem instance I. Right, so now this completely specifies the performance measure of each of the algorithms. Okay, and to be concrete, because by now, again, I kind of talked at a high level with pictures and everything, let me give you an example, and this comes from a paper by Tim Rabgardhan and Rishi Gupta in 2016. So here's a very concrete, simple example to keep in mind. It's an abstract problem that probably everybody here knows. So you have as input an instance I that consists of n items. And each item I has a value vi and the size is I, and we have an abstract capacity C. And when the abstract problem says, select what the output should be is the following: select the most valuable subset of items that fits in the knapsack, meaning find the subset B of the set of items that maximize the sum of the values of the items in the set, subject to making sure that they fit in the knapsack. Okay, so that's a concrete algorithmic problem, and now here's a concrete example, because I want to give a concrete example of a parametric family of algorithms. So for this problem, a parametric family of algorithms that was studied in this paper is a very simple family of greedy procedures. Each algorithm in the family is parameterized by a real valued number, alpha. And so for every alpha, the algorithm alpha does the following. It's basically a greedy algorithm. And so what we do, we first set a score for each item I to be vi over si to the alpha. So if alpha is 1, this is like bang per buck, right? But in general, alpha might not be 1. And then, so we first set for each item I a score to be vi over si to the alpha. And then in the decreasing order of the score, we add each item to the knapsack if there is enough capacity left. Okay, you can kind of convince yourself it's very easy to show that for different instances, different values of alpha lead to different solutions, and there is no value of alpha that is good for all instances. Okay, and so this is a concrete example of a parametric family of algorithms, and Here, what I didn't tell you yet, but let me mention is what's the utility function. So the utility function here is the solution quality. So U of I and alpha is the value of the item chosen by the algorithm, parameterized by alpha on instance I. Okay, so here is the solution quality. Okay, so this is a concrete example of an algorithm problem with a concrete family of parameterized greedy procedures. So it's a family of algorithms. Now going back to the general framework, so like this is a statistical learning framework for data-driven algorithm design. So basically we have, so as I mentioned, we want to do data-driven algorithm design. So we want to learn an algorithm that dwell on a specific domain. And so how do we model the domain here is for unknown distribution of our problem instances pi. So this is when we do statistical learning. And so we assume that when the training algorithm, so we have a training algorithm for learning a data-driven algorithm. So we assume that our learning procedure uses MIID samples of problem instances drawn from this fixed unknown distribution of our problem instances. And the goal is to find an algorithm, A alpha, from this large parametric family of algorithms that hopefully does all on future instances of the problem, future instances of the algorithmic problem. And here we also assume that we can measure the corresponding performance measure U alpha of I for each algorithm A alpha on each input instance we might care about measuring in the training set. Okay, so there is a fixed distribution of a problem instances. We assume that in the training phase we get access to IID samples coming of problem instances coming from this distribution, and then the goal is to output an algorithm that performs almost as well as the optimal algorithm A alpha star from this family. And this is a family that the algorithm A alpha star is the algorithm that maximizes the expected utility, maximizes over all algorithms A alpha in the family of algorithms, the expected utility of the algorithm A alpha on an instance I drawn at random from the given distribution. So this is the optimal algorithm A alpha star is the optimal algorithm that we are trying to compete with based on samples of instances coming from our domain. And notice, actually, as opposed to average case analysis, where you typically assume a very specific type of distribution of our instances, here we just assume that the distribution exists and that we can sample from the distribution. So it's in a way more flexible. Okay, and now one way to solve this problem, to find a data-driven algorithm, is to, like, what else would you do is to just pick an algorithm A hat that does all over the training set of typical instances. But as I mentioned already a couple of times, when the very important question that arises is how large should the training set of typical instances be so that we can guarantee that this algorithm A hat will also do well on future instances. And the key tool that we're gonna, I guess, focus on this talk, there are other tools, but the key tool that I'm gonna focus on this talk is uniform convergence guarantees that again come from statistical learning theory, that roughly speaking, they are bounded the form how large should the training set of typical instances be in order to guarantee that with high probability over the draw of the training set of typical instances, we have it uniformly for all algorithms in my algorithm family ALG, their average performance over the training set of typical instances is close to their expected performance overall. And if you think about it, once you get uniform convergence, then this immediately guarantees that the algorithm A hat that does the best or nearly the, if you have an algorithm A hat that does the best or nearly the best over the training set of typical instances, the algorithm A hat will have a high expected performance on future instances as well. Okay, and now to get this uniform convergence results, as I mentioned, basically mathematically look like this. I described them in words earlier, but this is how they look mathematically. To get the key point to get such uniform performance guarantees, we need to analyze this intrinsic learning theoretic notion of complexity of the induced family of utility functions, essentially. Okay, and like here are, and there has been, okay, so, and the way this literature evolved initially, including in papers with my students, in the original paper by Tim, not original, but in one of the early papers by Tim Ravgarden, he analyzed, for example, the notion of complexity for greedy procedures, for knapsack problem, when with my students analyze it for other families of problems like clustering and branching, like branch and bound, branch and cut for solving mixed integer programs, and so on. So we first look at case studies, but after a while I realized there are very general principles. You can write generic theorems that then you can apply on your favorite new data-driven algorithm design problems. And so there are a couple of results in this literature, so you can write down very general abstract theorems based on what I call dual function classes that I'm going to describe now. And now I'm going to present one of these theorems, and there are a couple more that I'm going to mention towards the end. And the beauty is that these theorems are very general, and you can apply to your favorite data-driven algorithm design problem. Okay, so basically, these techniques give us a bound on the learning theoretic notion of complexity for the family of functions that we really care about. And the family of functions we really care about are these functions u alpha of I, right? For each algorithm A alpha, I have the corresponding utility function u alpha, right? That takes as input instance of the problem and tells me what's the performance algorithm A alpha on instance I. So this is a goal. Our true goal is to show that this notion of the learning theoretic notion of dimension for this family of functions u alpha is small, because if it's small, the uniform convergence bounds from statistical learning theory will tell us that we don't need too many samples to generalize. So our goal is to come up with a notion of to bound the dimension of let me call this primal function class. These functions are parameterized by alpha and take as input instances of the problem. Now, a lot of what these theorems do, they show that they give a bound on the learning theoretic notion of complexity for this primal family of functions as a function of the structure of the dual function class. And what are the functions in the dual? For the dual function class, what I'm going to do instead, I'm going to fix an instance of problem I, and I'm going to vary the parameters alpha. Okay, these are the dual functions. And so what these techniques, roughly speaking, they give us a bound on the learning theoretic notion of complexity of the primal function class as a function of the structure of the dual function class at a high level. And right, and this is a result, for example, from a paper that I had in STOC with several co-authors, Dan de Blasio, Carl Kingsford, my former student Travis Dick and Erland Wittersick, and Thomas Handel. And this is the first time when I kind of wrote a general theorem that abstracted many of the results in the literature. Okay, and you might wonder, what results does it really abstract? And so, like, for example, why would I care about, why did we write this abstraction? Because again, as I mentioned, for many of the data-driven algorithm design problems, for many of the case studies, turns out that if you look down in the proof, what happened, the dual function classes are piecewise structures. So for example, for the knapsack problem that I described earlier, right? For the family of greedy procedures for solving a knapsack problem, what was shown implicitly in the paper by Tim Ravardhan and Rishi Gupta was that if you fix an instance of the knapsack problem, vary the parameters alpha of the parameterized family of greedy procedures, this dual is piecewise constant. So it might have sharp transition boundaries, because if I slightly switch the parameter of the algorithm alpha, I might include other items in the knapsack, so I'm going to get a completely different solution of a completely different cost. But this doesn't happen too many times. In particular, this, you can argue it only happens, roughly speaking, n squared times. So these sharp transition boundaries there correspond to moments when if I slightly vary alpha, I'm going to pick one item versus another item in the knapsack. Okay, so for the knapsack problem, the dual is piecewise structure, but turns out the same happened in many other cases. So for example, if my former students, we looked at parameterized families of greedy procedures, and then where you are trying to learn how to link, and maybe learning how to do dynamic programming on the top to solve clustering problems. And again, there also, the corresponding loss functions was piecewise constant. In other scenarios, we looked at for example, like similar other scenarios like learning how to price, or learning auctions for revenue maximization. Again, the loss functions are piecewise linear, for example. So for example, if you are doing item pricing, you are trying to do item pricing to maximize revenue. Now you have more parameters, not only one like for the knapsack problem, because you have one price per item. But you can argue that the corresponding revenue functions, if I fix an instance of the problem, vary the prices, the corresponding instance will be piecewise linear in basically high dimensions, or the number of dimensions is the number of items. Or another kind of cute example was like if you learn how to round semi-definite programs, so rather than just doing the Gomez-Williamson rounding procedure that gives you the optimal worst case approximation guarantee for maxcut, if you want to do a data-dependent rounding, where the loss function was piecewise inversely quadratic. The dual loss function was piecewise inversely quadratic. So in a number of applications, turns out that the duals are piecewise structured. So it's like, it's time to now write a general theorem, and that's exactly what the theorem that I showed you does. How many more minutes do I have so that I know how to? 7 minutes, okay, good. So Okay, cool. So I guess I'm gonna now try to show the theorem. So, but before showing the theorem, I want to mention like the technical details. What's the notion of dimension that we are using? It's a generalization of VC dimension. So what's the VC dimension for binary valued function classes is the cardinality of the largest set of items that can be labeled in all possible ways by function in the function class. So for example, VC dimension of linear separators in R2 is 3, in RD is D plus 1. And now we are trying to talk about learnability of real value function classes. So we're going to talk about generalization of it, the pseudo dimension. And what's the pseudo dimension? Really, I'm not going to go through the details now, but it's kind of roughly speaking is a VC dimension of a very related class of functions, the VC dimension of the class of below the graph indicator functions. So you start with the original function class and can define a binary valued function class that is just the function, the most natural binary valued function class induced by the original function class. And the VC dimension, the pseudo dimension of the real value function class is the VC dimension of this binarized function class induced by the F. And you can get sample complexity bounds based on the pseudo dimension. And so since I only have 7 minutes, I just want to show you, for example, more precisely how this theorem looks like. So, what the abstraction is. So now imagine that we're in a situation where we're trying to bound the pseudo dimension of the primal function class. So these are utility functions for algorithms A alpha parameterized by alpha that take as input instance of the problem. And we are trying to bound the pseudo dimension, the learning theoretic notion of dimension for these functions U alpha. Now what we show is that if instead the duals, so now I fix an instance of the problem I and I vary the parameters alpha, and these duals are piecewise structured like in this picture here, where I can put down some nice boundary functions. So this is a parameter space, and I can put down some nice boundary functions, these dotted boundary functions F, so that inside each piece induced by these boundary functions, the utility Ui of alpha is again nice, comes from some function class G, then we can give a bound on the pseudo dimension of the primal function class as a function of the niceness of these boundary functions and the niceness of these functions inside the piece. Right? So pictorially speaking, if these duals are piecewise structured, then I can give a bound on the pseudo dimension of the primal function class as a function of the niceness of the pieces and of the boundary functions that give me the pieces. Okay, and I'm not going to go through the details. Come and talk to me offline because I only have very few minutes left here. I'm not going to go through the details, but the proof is actually very cool. Once you have the right level of abstraction, the proof actually, if I had time, it would be a slide. It took me 5 minutes to go through it. It's actually simpler than the proofs that were there before for the various case studies, because once you have the right level of abstraction, you know exactly what to apply. We use kind of a combination of Sauer's lemma on the primal and Sauer's lemma on the dual, and counting, because in the end, the pseudo dimension of this dimensional combinatorial algorithm is intelligent counting, and you get the desired bound. Okay, and again, come and talk to me offline if you're curious. The exciting thing is now this general theorem applies to all, basically to all of the case studies for data-driven algorithm design known before, but also it applies subsequently to many others. So like for mechanism design, operations research, as I mentioned, learning to branch, learning to cut, and learning to cluster, and learning to price, and so on. And one thing that I didn't mention, by the way, but I was assuming is implicit, so actually you can also do experiments. And so for example, for learning how to cluster, as my students have shown, this is old experiments for more than 6-7 years ago, you can actually show that, for example, there is no single unique linkage procedure that does well on all data sets, and it really makes a difference if you learn how to link, for example, right? And so you can show this experimentally as well. I mean, this is the whole premise of this line of work, but you can easily show it experimentally on many of these domains. And how many more minutes do I have? 3 minutes left. Okay, cool. So since I have Piotr here, I want to also mention one of his results. So I presented, right, so as I mentioned, we have this general theorem that I presented where you could give a bound on the pseudo dimension of the primal as a function of the structure of the dual function classes. Now, Piotr and Peter Bartlett and Tal Wagner had a call paper where they had similar results, just that they didn't quite phrase it that way, but it's still a bound. You can think about it in the exact same way. So now what they say, if for every dual, so for every now dual is parameterized by an instance I, and if for every dual I can decide whether, as I vary the parameters alpha, I can decide whether the dual function is above or below a threshold z by using some sort of GJ procedure, which is just looks like a decision tree where the decisions are given by ratios of polynomials. And if I don't have too many like I don't have too many nodes in this decision tree here, then I can again give a bound on the two-dimensional, the primal, on the learnability of the family of algorithms as a function of how complex these polynomials here could be and how many of these polynomials I have here in the largest decision tree that describes a dual. So actually, you can think about this also as being a theorem via dual function classes, or giving a bound on data-driven algorithm design via dual function classes. It's often useful in situations where you can have a more explicit description of this family of algorithms. Like, for example, we don't know how to apply for learning how to branch or learning how to cut, but you can apply it in many other interesting cases. And my students have applied either of them in different situations. And in fact, we also have a recent generalization of this, in the work by Piotr and Tal Wagner and Peter Bartlett. They wanted the ratio of polynomials in our decisions here, but we also have extended it to something called Pfaffian functions, where we also allow exponentials and logarithms in these decisions here. Okay, now basically, if you take together all these theorems, now you have very general tools for analyzing data-driven algorithm design. So if you have a new parametric family of algorithms, if you're trying to learn an algorithm based on data, the very first thing I would do would be to try to apply these tools, and often you immediately get some interesting result. And actually, I think they also should be applied more frequently. So, and people have applied them for data-driven algorithm design, but also they should be applied more frequently to learning predictions or algorithm predictions. Because as I mentioned, I will talk about that, and some of the other speakers in the workshop will talk about that. There is kind of the parallel line of work on algorithms predictions, but they're often the learnability of the predictions part is ignored, but I think that these tools should also be applied there because, what's a prediction? It's just, you can think it's a parameter in a certain sense, or a hyperparameter, and you can hope to apply these tools. And in some of the works, some of my former students, like Misha Kodak, have successfully applied them also in the context of learning predictions for algorithm predictions. Okay, and I'm gonna, because I only have 2 more minutes, I also want to mention, so far I mentioned about data-driven algorithm design via statistical learning. You can also consider doing online learning. Things become even more non-trivial because now you have, again, the loss functions have many sharp transition boundaries, and now you cannot even give worst-case guarantees for online learnability because in the worst case, if you have sharp transition boundary, no regret is not possible. And so we have a line of work where we give sufficient conditions on how these discontinuities of the sharp transition boundary of the loss functions should look like. Maybe they should not be too concentrated, they should be dispersed, and then learnability are possible. Okay, so I'm skipping this so because of lack of time. But the key questions to think about when we do data-driven algorithm design is what are interesting tunable family of algorithms, and then once you have this interesting tunable family of algorithms, then you can hope to apply some of these general tools to analyze them. Okay, and I hopefully do have 1 minute left. I also want to mention one thing. Because now we use machine learning and AI for data-driven algorithm design, but who designs good machine learning algorithms? Right? If you think about it, machine learning algorithms themselves have tunable hyperparameters. Any machine learning algorithm comes with hyperparameters. And who tunes the hyperparameters? Well, students, engineers with a lot of experimentation and a lot of resources can automate it. Okay, and so in other words, can machine learning fix its own problems? Right, and this is another line of work that some of my students have worked on, including Dravi that sits here. He will have a poster about that, like learning how to tune the parameters of gradient descent. But you can ask this question, can you do hyperparameter tuning of machine learning with provable guarantees? And the cool fact that these dual function classes I told you about, we are able to apply them for many of such family of machine learning algorithms. For example, the most recent work, some of the recent work learning how to build decision trees, if you care about interpretable machine learning models. Ravi again here had the student paper award at UAI on that, or maybe learning hyperparameters of neural networks. So the cool fact that these dual function classes I told you about can be now used back to analyze machine learning algorithms themselves, hyperparameter tuning of machine learning algorithms themselves. And things become more, I would say even more non-trivial there. So for example, if you are talking about tuning the hyperparameters of neural networks, there is an additional difficulty because typically in these scenarios, I want to learn the hyperparameter based on past instances, but on a new instance, I still want to tune the parameters themselves. And so arguing that the dual function classes are piecewise structure becomes much more challenging. But we are able to do it in certain cases, for example, for neural networks, if the parameter-dependent dual functions are piecewise structured. So again, come and talk to me if you're curious about that. I guess I'm going to stop here because I guess I'm running out of time, but I guess data-driven algorithm design is a very exciting field, helps thinking about designing problems in a data-driven way for problems coming from theory of computing, but also we can go back and think about learning machine learning algorithms themselves, hyperparameter tuning of machine learning algorithms themselves, and I guess also to end in an even broader, I guess with a broader perspective, I think it's also very interesting to think about agents for algorithm design, AI for algorithm design, right? So a lot of what I talked about today, we assume that how we use machine learning or AI, we use past instances of the problem, and we tune, and we basically, I guess, learn algorithms that leverages past instances of the problem. But when we talk about agents for algorithm design, there is additional textual feedback, additional interaction between the human and the machine learning system or the AI system, and it will be very interesting to kind of provide provable guarantees for those scenarios as well. Okay, so I'm going to end here, and I'm happy to take any questions.
So if I understand correctly, like most questions here, most techniques here are based on uniform convergence and numerical optimization. Like, can I use some other algorithm, like instead of TRM, to get like much better sample complexity? Is there like work on those kinds of directions?
So that's a big question. So let's see if I really it's a great question. I mean, this is very cool. Like you are asking if anybody has done it. So I think this is what I showed here is mostly by two-dimension. You can also done some analysis for random complexity, but not at the same level of generality. We have specific cases where we can analyze random complexity, but there's still ERM or approximate ERM. And in fact, this technique is one thing I was going to point out. They also apply to if you have tune the algorithms by hand somehow. Right? Like we are kind of uniform convergence, either data independent or data independent uniform convergence. I think it'd be very interesting to also do maybe coupling arguments. Yes, so there could be other tools for version. We do analyze the online learning as well. But as I mentioned, on online learning, we need even more conditions. But the whole thing, of course, would also consider your there are also some online techniques. But we consider also coupling arguments and box. Yeah.
So the parameterization, some of those parameterizations seem ad hoc. Like why is that interesting for knapsack? Like why are only those tools interesting?
That's great. Actually, in fact, that's a great question. So maybe let me mention. So in some cases, that's actually a good question that you even think about. What are interesting tunable primitive algorithms? And what we've done, sometimes there are people, others people use in practice. Like for example, learning how to do decision trees. That is to the paper or to the right or that. There are things that we use in practice, like use Gini index or use ID values or some other heuristics. You can pull out, you can find primitive algorithms and abstract all of those heuristics in practice. And you can learn the best from the family. So it's kind of already better than what people do in practice, in a certain sense. So sometimes you can come up with the primitive algorithms, maybe in capture when people do in practice, so outside of the way. But you can also sometimes have a distance when they are writing the reasons to begin that they are good primitive algorithms. So one example I did 10 years ago in the code, and I thought about some email, like learning about cross-identity program. In the family, like the Golden Swimmers algorithms, but it's kind of it's surrounding the margin-based surrounding. And it was non-analytical from we 5 years, sometimes it's like the distribution of, it's better to use margin-based rounding, but nobody else how to learn how to round. Sometimes you may have analytical reasons to consider a primitive algorithm, sometimes, you might have to do it in practice anyway. It's a good question, it's a key question, how do one with primitive algorithms? It's in a way on the art in all of these cases. Oh yeah, and concept analysis, I think the analysis demonstration doesn't provide the reader to be a knapsack, the reader of general knapsack, just from King's paper, and I think they claim the trick is sometimes different alpha work better in settings. So for example, I think for alpha equals 1 sometimes works well, alpha equals 2 also, and so on. So even though it was observed in practice, different alpha work better in settings.
Last question. Yes. Are there any implications of this like dual function theory you mentioned for like classical learning theory, or there will be an overcomplication given the complexity of the instances rather than the complexity of the function?
I guess by implication, I think because the typical learning can you often look at like classification, what we call the list, but but this is more like real-world function class. I mean, it's very interesting from a learning theory point of view. Meaning it's solve a lot of questions because with that learning theory, I don't know, but it's a cool theory, learning theory that basically. fewer bytes are, or I think it's cooler than fewer bytes are. Sometimes, like, I guess the one case what I know is, I guess, data clouds, I guess you are asking about the interesting applications that come from the microcomputers. I guess we show hyperparameter tuning for machine learning algorithms. It's very, it can provide very cool bounds in about these function classes, which I don't think it was even thought about before. Learning how to tune the regression problems, learning how to do decision trees, learning the hyperparameters, learning the activation function for neural networks. Like we can explain what the variables involved are, where we use actually tools from these neural function classes. And in some of the cases we use the algorithm and the neural function class despite production, some other cases that we use pure using the DJ framework. Run is an expert to decide which one is better because of different settings. Yeah, so I guess the answer, yeah, actually had a big implication. I remember the machine learning because of the implications. For me, you think find other implications. Let's call that more massive learning.
That's nice.